Hello, your interview question is below. Write code in this pad like you normally would, and your AI interviewer will be able to see it. Largest connected component over time. Given a graph has a number v of nodes and a list of edges where each edge is a triplet, uv time, where u and v are nodes between 0 and v minus 1 inclusive, and time is a positive integer representing the time when the edge was added to the graph. We are also given a sorted list times with positive integers. Okay, return an array with the same length as times with the same size with the largest connecting component at each time in times. Here we have an example. N is equal to 4. Where's n defined here? Well, we have edges 0, 1, 60, 0, 30, 180, 2, 3, 120 times, and then output 1, 2, 4. What does this n mean? Given the graph has the number v of nodes and a list of edges where each edge is a triplet. Okay, so that's why we have triplets. Your v are nodes between 0 and v minus 1. Okay. Time is a positive integer representing the time when the edges was added to the graph. Like this is the edge added. Okay, added. We are also given a sorted list times with positive integers. Wait, what? Okay, returning an array with the same length as times with the size of the largest connected component at each time in times. A bunch of constraints here. Now, n is equal to 4. Is that number of nodes? I think so. I'm not even like looking on this chat on the side. I'm just like, I just have the microphone on. I don't know. Okay, hold on. So why is 1 the largest connected component at time 30? Largest connected component over time. 0, 1, and then 60. And time is a positive integer representing the time when the edge was added to the graph. Largest connected component at each time. So we have 4 nodes, 0, 1, 2, and 3. 0 and 1 have a connection. With the size of the largest connected component at each time. So I guess at this point, 1, none of the edges are actually formed, so just like the most you can have in a graph, Henry. The largest connected component. Yeah, the most you can have in one kind of component or graph or however you want to kind of call it is just 1. And then at time 120, there's this 0 and 1. Okay, so now 0 and 1 are connected, and so this number of nodes and like the largest connected component is now have like it's now of size 2. And there's also this 2 and 3, which is separate from 0 and 1. I'm wondering if 120 is an edge case or not. I think it's, I mean, even if it's not, there's still like, 2 and 3 just make a component of size 2, and this is another component of its own. And then when this happens, 0 and 3, then it connects like all of this, like all 4 of those components, and now there's the size of 4. Okay. Now let me take a look at the know if I'm gonna break the. Oh yeah, it closed the microphone. Maybe I shouldn't overuse it. We have where was I with this? I want to confirm the time times a positive integer representing the time when the edge was added. We are also given a sorted list times a positive integer. Return an array with the same length as times with the size of the largest component as each time in times. Okay, so that was one of my questions right there. Yeah, I think they actually answered it right there. One of my constraints, the rest of the constraints are there as well. V minus 1, so it can be 0. Anything else I should be considering? Why is there so many constraints? Oh, I guess, yeah. Sorted, does that mean non-decreasing, or does that mean, what else does that mean? Right, it's just increasing? So it says non-decreasing, interesting. All right, let me try and, first of all, let me change this to Swift. And then let me try and we're at 8 minutes. What's the next step? So I went through the question. I went through the example that was given. Can the number of edges be nothing? Can time be nothing? Time is in non-decreasing order. We did know that. Can we have, I'm assuming this times is a positive integer, so it's bounded by that. Does a 0 count, or okay. Well, how would I actually go about solving this? Like this entire kind of thing, I kind of went through the example and talked about how I understood it as a human at each stage. Are these edges sorted by time? I'm assuming not. Like these, like in our case, oh yeah, it's not sorted at all. So, what are some things I've noticed? First of all, I should probably write the boilerplate code. Yeah, let me write some boilerplate stuff. So let me just write function. Largest component, I'll just call that. Okay, and then this largest component we're given are we given the number of nodes? We're given times, which is integers. Okay, we're given edges, which are like nested like that. And are we given, and as well, given a graph as a number of v of nodes and a list of edges where each edge is a triplet, where u and v are nodes between 0 and 1, and time is a positive represented. We are also given sort of list times of positive integers. Return an array with the same length as times with the size of the largest connected component and each times times. Are we given n as a parameter to our function? If yes, then, or maybe we're given a graph. No, we're not given a graph. We're just given n. Maybe based on the problem description. Also get n, the number. of nodes. Okay. And then at each stage of times, we'll need to like do some kind of mapping. So at 30, right? At 30, we can go through this entire edge, yeah, the entire edge, and after we go through this entire list, we check whether or not it's less than 30, right? Is 60 less than 30? No. 180? No. 120? No. So there's no like there's no like component that's actually made, right? And then I guess like the way we know that is like we probably have some kind of like a hash table, like a mapping of some sort, saying that hey, like we have different nodes like 0, 1, 2, and 3, and none of them map anywhere else. Okay? And after we go through all of them, we go to 120. We see there's 60 and 120 here, so we make a mapping between 0 and 1 and 2 and 3. And then I think we would run depth first search on 0 and 2, and then see what the size is for each. So this is gonna be very it's gonna be very time heavy, like what I'm kind of listing out here. But it is okay. So after we do the mapping, right, 0, 1, 2, and 3, and then we do depth first search to figure out the size. Then we want to output the size, the maximum size, right, into the output. And the same thing for 4. We can do it all again, right? We check through all of it, and I mean we're kind of wasting time here. We're checking this and this again when it's not really needed to be checked anymore. Like now it's just this that needs to be checked. And that's added to like the hash mapping from 0 to 3. Then we do a DFS on 0. Again, duplicate work. I feel like this is like, well, first of all, going through this entire like case, worst case O of n, going through it once, and I think that the depth first search can add another n, like worst case O n squared. I'm not sure how to calculate those like depth first search calls, like how deeply they actually go into the stack and all. But I'm gonna assume time collects the O(n) squared. Is there a better way to do this? I wish I can speak. I've lost my privilege to speak after because I spammed them. Oh my. What other solution can I think of? How about, so we're using the hash set to create some kind of a graph. Can we not just save the size of the components while we're at it, or yeah, I don't know. I looked at the first constraint here. Probably shouldn't have, but I did. But why does it say 1 here and then 0 here? Oh, that you're like labeling the nodes like that, but there's at least one node in the end, or in one vertex, however you want to call it. I can't think of a more optimal approach, to be honest. Um, oh man, I'm going silent when I shouldn't be going silent. Sorry about that. Let me try and voice out my thoughts at the moment. I don't know if I'm going in the right direction or not. I kind of just want to save this and try and like prompt this interviewer to see if I can get anything useful. Let me try refreshing. Okay, it's gonna revert that. Yeah, am I still in the same question? I am still in the same question. And then just do that. Okay, and then let's try this. Okay, so I'm currently at the stage of thinking about my algorithm, and right now what I have so far is I'm gonna go through this edges array for every single time that's here, and then I'm gonna have like a hash set to kind of create a graph, and to actually calculate the size I would have to like do depth first search on each of the nodes. Now I think like going through the graph, going through like edges for example is already O of n, and then the depth first search I'm not too confident with my recursion skills, but I think it's another like n, so like time complexity O n squared, space complexity O of n with the hash set. Can I kind of optimize this further, or do you just want me to kind of begin coding because we're at 19 minutes now? What do you think? I'm gonna close that. That's a reasonable starting point. Can you walk me through what you mean by go through the edges array for every single time? How would you determine which edges should be included in the graph at every query? I was supposed to be getting your approach clear first before dumping the code. You mentioned going through edges for every time. That's something you're thinking about processing every query time separately. What do you think would be the time complexity of that approach? Didn't I explain the time complexity? Yeah, good question. What I'm thinking is you mentioned going through edges for every time. That sounds like you're thinking about processing every query time separately. What do you think would be the time complexity of that approach? So it's the time complexity would be O n squared. Well, I don't think it's. Oh shoot. O n squared. So to break it down, you want to, if you go through the edges, right? The edges, there's worst case, there can be n. Honestly, even more if you're like this. I'm assuming edges mean vertices plus edges. Okay, so O of n, and then if you have to go through depth first search, then that's n squared. Let's see if they understood. Otherwise, I'll just kind of go on my own way. Oh, yeah, it's having a really hard time understanding me. my approach is going to be lengthy. Like it's going to be a tough one. I'm not going to lie. Okay, what I'm going to do is I have no code written out. I'm going to continue having my discussion right with the interviewer. I'm not going to worry about writing the code for this one. Okay. So when you say you need to go through edges and then do a search, what exactly would you be searching for? I'm going to go through the edges, and then as I'm going through the edges, sorry. Let me rephrase that. So I'm going to go through times, okay? And when I'm on time 30, for example, I'm going to go through all the edges in the edges input that were given and see if any of them happen by the time that I'm currently at. So when I'm at 30, are there any edges that have been created by time 30? And you see there isn't, right? That's what I mean by, that's the relationship between times and edges. So time knowledge is added, so each size is none. Now continue with your question. What would you do at time 20? Yep. Now what's your effective? Let's see this. Okay. Now, after I've identified the edges that exist at a given time, add them to a hash set. So have a mapping from 0 to 1 and 2 to 3. And then run depth first search on 0 and on 1, or maybe it's 2. Whatever nodes there are, just run through depth first search on each one of them. Now this is problematic because it's going to be a lot of time complexity. Yeah, to avoid counting something multiple times, you'd have to kind of have a visited set or some kind of like a check, or like even check in the hash table in it. Actually, let me think about that actually, because the values are already there in the hash table. How would you avoid checking it twice? I think then the visited set would be the right way to go. I was thinking of a different question where they used the hash table to determine whether or not to continue forward. But yeah, like a visited set would be the right way. Okay, so putting this all together for every query, you're filling the edges of the graph, then use the visited set to find all the kinetic components. Now think about the time complexity again. But up to 10 to the power of 6 query times, what do you think about the efficiency of this approach? What's the time complexity of depth first search? For me, that's O of n. Okay, and then going through all the edges, that's also another O of n. So I'm thinking O n squared. O n squared. Okay, so I'm not doing this correctly then. So let's be more precise with the variables. Okay. I love how it's really trying to drill down and get me to specify, really like be specific with my understanding. I like this. This is good. You're getting closer. Let me break this down. Depth first search on a graph is O vertices plus edges. Yeah, where vertices is where V is the vertices, E is the edges. You might need to do this for every query time. You have up to 10 to the power of 6 query times. So what would the total time complexity be when you multiply these together? So yeah, this would be O. So assuming query times is Q, this would be O Q times v plus e. Oh, okay, it already said that before, my bad. So, do you think, what would be a more efficient approach that doesn't require rebuilding the graph from scratch for each query? Now, what observations can you make about the relation between query times and how the graph evolves? Is there anything you notice about how edges are added over time? Yeah, do I notice anything? That could be quite expensive. So now what observations can you make about the relationship between the query times and how the graph evolves? So just one observation I'm making is that as the query times, as you're kind of going through the query times, the graph, like its components, kind of get bigger and bigger, so there's already a graph in place. So instead of creating a new graph from scratch, you can kind of add on top of it. I don't know how you would add on top of it, though. Like, it's just like at a conceptual level, this is what I'm thinking. So if you're building incrementally, what data structure approach might help you efficiently track connecting components as you add edges one by one? A linked list? Like I don't want to start listing out data structures and algorithms, or sorry, data structures in this case. But like I was thinking about a hash table. Would that not be an effective solution? Like I was thinking just a hash table. Is it gonna? Dragging connecting components as you add edges. That sounds like a tree then. Wait, what data structures have you learned about that are good for keeping track of which elements belong to the same group or set? What? That which elements belong to the same group or set? Graphs? Is graphs a data structure? I don't think it is, right? Trees? Graphs? How do you group things together? Tuples? I'm just listing data structures out now, which is very bad practice, but what so okay, hold on. So at a high level, I know this is about graphs. I don't think graphs is a data structure though. Like, do you want me to think about like something more specific than graphs? I'm just trying to get some information out of the AI interviewer. Groups or sets? I really good answer was like, well, are these tuners in the same connected component? What is that? I don't know, man. Deal with disjoint sets and unique operations. I have not. What? Are you referring to sets? Am I? You mentioned union operations. That's a good clue. No, you mentioned union operations, bro. What is your support operations like union to merge two sets and find to determine which set an element belongs to? I have no idea. I have not done I've not done this stuff. Operations like union to merge two sets and find to determine which set an element belongs to. What in the world? Okay, I'm gonna list them out. Okay, I'm just gonna list out my thought process because I'm kind of stuck with this int. Okay, so there's linked lists, right? There's hash tables, hash maps. There's stacks, queues. There are lots of data structures. What other data structures? There's trees. There's probably other heaps. Maybe I need like a collection or a group. Yeah, I'm blanking out. My God. I seen union find in one question before. I forget what data structure they used though. Let me stop you right there. It sounds like you haven't got a union find before. Sure. Let me interesting. Union find. Oh, I gotta search this up. Union find. Data structure. Disjoint set data structure. Is that a topic I've covered? What in the world? What is this topic? Union find data structure. What is this? What? Is this part of prefix sums or what? Like, I need more information. I'm going through my Cracking the Coding interview book. Set a map implementations, union find, there we go. Yeah, this is a very extra topic. Okay, I'm not gonna continue on with this. I'm gonna leave it there. I think it was good problem solving, good to think about the concepts and everything. Yeah, I'm gonna leave it there. Okay. Let's see what my score is. If they give me a score, let's see. Probably like 0 on coding. I think my communication was decent, like 3. I'll give myself like a 3. 3 out of 4, okay. Yeah, fair enough, 1 out of 4. Problem solving. Missed the optimal union find solution despite hints. Well, that makes me feel terrible. I'm sorry. You're demonstrating good understanding of graph traversal concepts and correctly analyze your approach to complexity. However, you need multiple hits to reach basic insights and then implement any code. Yeah, okay, well, that's fair. Okay, cool.